Hi folks, and welcome back to Physics with Captain Rod. I'm making this video here to help you out with numbers 22 and 23 in your Unit 2 homework. So let's see, what do we got here? Young Timmy, boy, we've never seen him before, huh? Standing on top of this building, throws his ball nearly straight into the air, and it lands in the hole shown. So basically, the idea is the ball did this. So standard rule of thumb when using principles of work and energy, make sure you draw the system at each state and label each state. So we're going to call this state 1. Ball's moving upward at some velocity, right? And let's call that V1 because we're going to have multiple velocities in the problem. All right, so the ball does this. Now here's a picture right before impact. Let's call that state 2. Velocity is down. We'll call that V2. Now you notice there's some daylight there. That's deliberate. We're going to write our equations an instant before it hits the ground. Right, so it's still moving down at a certain speed. All right, now, if you want to apply principles of work and energy, you have to define a datum, and that's what I would do. Now, it's optional. Let's put a datum here. That's a great place to put a datum. When you write out the work-energy theorem, right, PE1 plus KE1 plus work equals PE2 plus KE2. You're going to have a PE1. It's going to be positive because you're a height of 20 meters above the datum. You're going to have a KE1 because the ball's moving at that point. I'll talk about the work term last. Your PE2 term. Okay, we're 5 meters below the datum. I would personally put something like minus mgh2 or something, where this is the h2. Now, if you put minus mgh2 for the potential energy term, you don't need to put a negative value in for h, right? The minus sign already takes that into account. And then the KE2 will be a 1/2 mv squared. Okay, work terms. Always draw a free body of the object. And the ball only has one force on it, throwing out air drag, the mg. Again, if we throw air drag out. And it doesn't matter if the ball's on the way up or the way down. That's the only force acting on the ball. Now, that ball does, or I'm sorry, that force does do work. But that's what the potential energies take into account. If you tried to put a work term in for it, you're going to have mg times this distance right here. And effectively, the difference between those two potential energies is going to do that for you. So that force is already taken into account, and there's no other forces to worry about. So there's no work term. So that should get you through that problem. Let me get rid of all this stuff here before I move on. All right, so let's take a look at the next one here. Actually, there's a part B there. I'll let you folks worry about part B and whether or not you think that'll make a difference. I don't want to do that for you because the explain part is for you folks. So now we got Timmy riding this roller coaster doohickey thing here. And I believe in the problem, okay, the horizontal surface is rough. So what that's saying is basically we're going to worry about friction in this region. But friction is negligible in this region. We're not going to worry about it here. So let's see, part A, Timmy's speed at the bottom of the hill. Okay, this is just a classic work energy type of situation. Put a datum right here. Write out the PE1 plus KE1 plus work equals PE2 plus KE2. And you'll be able to solve for Timmy's speed at the bottom pretty easily. Okay, the next part. Whoops, darn it, sorry about that. The change in potential energy of the Timmy cart system. I'll let you think about that. But I will just mention this. Change in anything is final minus initial. So ask yourself, what is Timmy's final potential energy when he's here? Minus what was his initial potential energy when he was here? And you should get some negative number, by the way. Next term. how much work did gravity do as Timmy moves down the hill? Okay, so the gravitational force is down, equal to mg. And the displacement in the vertical direction is this 20 meters. And then ask yourself, is the work done by gravity positive or negative? Right? And remember, the force, when the force is in the direction of motion, the work is considered positive. And then the last question, what average force stopped Timmy over that 15 meters? So that's talking about what's happening between 2 and 3. Now, remember, at position 2, Timmy was moving pretty good. You found that in part A. What you can do now is write a work energy equation between positions 2 and 3. Right? Now, there's no changes in potential energy, so your PE2 and your PE3 are both 0, no problem there. You're going to have a KE2 term because at position 2 here, the Timmy cart system is moving pretty fast. Your KE3 term would be 0. And you're going to have a work term now, right? And let's talk about why. Look at the free body of Timmy and the cart. Right, you've got a gravitational force down. Right, the cart is supported by the ground. And there is a frictional force or some sort of resistive force acting on the cart, which is now to the left, because again, the cart is sliding left to right. So one of those will produce a work term, and it's not this one, and it's not this one. And the work is going to be negative because the force is to the left, but the cart's moving to the right, and the distance was given. So write out a work energy theorem. You'll have a KE2 term, and you'll have a work term, and you'll be able to get that frictional force from the work term. So that's probably enough on that one. I hope that this helps. Have a great day.